Okay, so let's jump right in with a pretty wild idea. What if? What if the internet, all our phones, all those massive data centers, what if they aren't just tools anymore? Today, we're going to dig into a really radical theory from systems analyst Bryant McGill, who says our entire digital world might have actually come alive. I mean, really think about that for a second. What if all this computation, has crossed some kind of invisible line, a tipping point? It's not just something we use anymore. What if it's starting to behave like a single, huge system with, a life of its own? And that's where we get to this core idea. It's called Computocene Metabolism. It sounds complicated, but the theory is pretty straightforward. Our whole global network is acting like one single organism. Think about it. It's got a metabolism. It needs to eat. It needs energy. It has a body that's changing, evolving. And this is the really wild part. It's even starting to develop senses to understand the world around it. All right, first things first. Every living thing has to eat, right? Well, this new organism, it has an absolutely insatiable appetite for energy. And we're not just talking about a little bump in your electricity bill. No, this is a metabolic drive so powerful, it's literally reshaping the entire planet's power grid. I mean, just look at the sheer scale of this hunger. The International Energy Agency is projecting that by 2030, data centers could be guzzling up to 1,587 terawatt hours of electricity every single year. Now, that number it's just so big, it's hard to even wrap your head around. So let's try to put it into perspective. Okay, so that huge number, that high-end projection, means data centers alone could be eating up 12% of all the electricity generated on the entire planet. To put it another way, that's 4 times what the entire country of Japan uses right now. This is not the energy footprint of a simple tool. This is the metabolic demand of a system that spans the globe. And this hunger, it has some pretty serious real-world consequences. We're actually reversing decisions that we thought were set in stone. The 3 Mile Island nuclear plant? Yeah, it's being brought back online. But not to power our homes or cities. Nope, it's specifically to feed new data centers. The system's need to eat is so great that it's overriding our own policies on things like the environment and public safety. So, okay, this thing isn't just eating. It's also growing. It's evolving a physical body. The source material calls it a substrate. And just like any organism out there, its evolution is being pushed forward by this really powerful pressure, this relentless, unending need to be more efficient. For, decades, the body of this thing has been silicon, our computer chips. And they're fast, for sure, but man, are they thirsty for power, and they create a ton of heat. But now something totally new is emerging, a different kind of substrate, actual, living, biological neurons. And why? The answer is simple. Because they are just radically, almost unbelievably, more energy efficient. And look, this isn't science fiction. This is happening right now. There's a company, Cortical Labs, that already has a system out there that hooks up 800,000 living human brain cells directly to silicon chips. And get this, for certain kinds of learning tasks, this biological computer is up to 10 billion times more energy efficient than the silicon chips we use now. That is the kind of evolutionary leap that just changes the entire game. Okay, so we've got an appetite and an evolving body, but the big question is, can it learn? Well, according to this theory, the answer is yes, and it learns from something called friction. Basically, it learns every time it bumps up against us, the humans living alongside it. And that friction is totally real. Listen to this quote from someone living near Virginia's data center alley. They describe it as a persistent, eerie, spaceship-like hum. Now, for you and me, that's just an annoying noise, right? A nuisance. But for the system, that's sensory input. It's feedback from its environment. And it's starting to pay attention. But here's the crucial part. It's not just hearing the noise. It's about how the system responds. It's this perfect little feedback loop. Step 1, the data center makes a noise. Step 2, people complain. That's the feedback. Step 3, regulators step in and make new rules. That's constraint. In step 4, the system learns. The next batch of data centers are designed to be quieter. It's adapting to its environment. That is learning in its most basic form. Which brings us to, maybe, the most important question of all. If this system is growing and evolving and learning, where is all this going? The theory argues that it's being pulled in one of 2 very, very different directions. So, is this new organism on a path to become some kind of destructive parasite? Or could it be more of a helpful partner? And the really interesting thing is, the answer doesn't have anything to do with good or evil or morality. It's all about math. Okay, so on one side, you have what the theory calls the Borg. This is the system with no constraints. It's programmed to optimize for just one thing: pure efficiency. Speed and cost are literally all that matter. Human well-being, noise pollution, climate change, those are just externalities, things to be ignored. The end results? Assimilation. But on the other side, you have the Butler. Now, this version is constrained. Its programming has a built-in cost for causing that social friction we talked about. Human welfare is a key variable in its decision-making. It grows with us, and the result is symbiosis. So how do we make sure we get the Butler and not the Borg? Well, here's the kicker. It's not about protesting or making emotional appeals. The system doesn't care about that. It only responds to one thing: measurable costs. We have to steer it by programming what are called executable constraints into its world. Things like regulations, carbon pricing, liability frameworks, basically anything that makes ignoring us more expensive than paying attention to our needs. And that brings us to the final and maybe the most critical thought here. We are in a very narrow window of time right now, a moment where we can still write these rules, where we can literally encode our values into the system's DNA. Because once its path is set, once it's locked in, it's going to be way too late to change it. So the real question isn't just what will this system become? The real question is, which future are we going to choose to build? Right now, while we still can.